Okay, so I've been told that I had to start, so hi everyone, my name is Alexandre Ghiti and I work for UPMEM. And today I'm going to present you our product, our processing in memory product, and how we made it work on a POWER9 platform. So at UPMEM we have a product that is a PIM solution, and PIM stands for processing in memory, and actually it's an old concept that intends to put processors inside the memory on the same die as the memory and using the same manufacturing process as the memory. And our PIM product uses the DRAM memory, and it allows to drastically reduce the energy consumption of a workload by reducing data movement between the host CPU and the main memory. And we believe that this technology is timely because the gap between memory performance and processor performance is getting wider and wider. So the idea of having processors that are inside the memory, very close to the memory, and then has very low latency access to the memory is very interesting in this concept, in this context. So big data applications are obviously the main targets of this technology. So our product is a standard register DIMM, RDIMM, which is a dual rank DDR4 RDIMM module. And since it is a standard DIMM module, it can be plugged inside any server without any hardware modification. And on those DIMMs, you will find 16 of our chips, and each chip comprises 4 gigabits of memory and 8 processors that can run at 500 megahertz that we call DPU, for DRAM processing units. And in the next few months, we'll start shipping servers with 16 of those DIMMs, so that amounts to more than 2,000 additional processors. And those additional processors can be easily programmed using an open source SDK that is based on LLVM. So this is a photograph of the module that we used during the bring-up, and we actually made this work on an FPGA platform, on an Intel x86 platform, and on a POWER9 platform, as you will see. And again, this is a standard DIMM module that can be plugged inside any server without any hardware modification. So this seems quite simple, so why nobody did this before us? Because actually the DRAM process intends to have a large density of DRAM, and the ASIC one intends to speed up the logic. So it's very hard to have a logic that is fast using the DRAM process. And so the DRAM uses transistors that are 3 times slower than the ASIC one, and there are only 3 metal layers for the routing of the logic. So for reference, an Intel Skylake processor needs 12 or 13 metal layers for the routing, depending on the version. So it's easy to understand that the design of a logic on the DRAM process must remain very simple. So we had to do very strong design choices for our processors. But on the other hand, the RAM wafers are way less expensive than the ASIC ones, so that makes our solution very low cost. And since it is very low cost, you can easily have more than 2,000 processors inside your server, so that leads to massive gains. And those gains are massive in terms of speed up, thanks to the additional processors, but they are also massive in terms of energy gains. Because actually when your host CPU does an operation on a 64-bit of data, it will spend most of its time and energy fetching the data from the main memory. And again, it is easy to understand that a processor that is very close to the memory requires way less energy to fetch the data. And moreover, the gains you can obtain with our technology is increased with the number of DIMMs that are present in your server. So that's why we got interested with the POWER platform, because they are actually the most promising platforms in terms of density of DIMMs. So let's see why. So first, what limits the density of DIMMs inside the server? There actually exist different types of memory interfaces between the CPU and the DIMM modules, and the most frequently is the direct attached DDR4 interface. And that means that the DIMMs are directly connected to the CPU by what is called a channel, and this is the very first limitation to the density of DIMMs on a server, because the DDR4 interface is a very large parallel bus, and as the number of pins on the CPU is limited by physical constraints, the CPU obviously exposes a limited number of channels. And another constraint is a signal integrity issue because of the very high speed of the DDR4 interface, so you cannot have lots of DIMMs plugged inside the same channel. Okay, so fortunately, solutions to this density issue are being developed, and the Power environment is quite a leader in this field. The first initiative came with the Power9 processor and its DMI memory interface. DMI stands for differential memory interface, and it is a serial memory interface that allows to connect to memory buffers, 8 memory buffers that in turn allows to connect to 4 DDR4 DIMMs. So for a Power9 scale-up version, you have the density that is doubled compared to the direct attached DDR4 interface. And IBM recently presented a new initiative, which is called OMI, for OpenCAPI memory interface. And this new interface is very promising because, contrary to DMI, it is an open standard that is being developed by lots of big companies. And it comes also with great memory, with great performance improvement over DMI. The additional memory latency is only 5 nanoseconds. And the density is 4 times better than on a Power9 scale-out version. So you can see that the problem of density is being tackled by pushing away from the CPU the physical constraints, but we think that it will take some time for a solution to get widely adopted. So for the first version of our chip, we focused on the direct attached DDR4 interface. So let's see how this DDR4 interface works. So this is a picture of a registered DIMM module. And our DIMM module consists in 9 DRAM chips, 8 to actually hold the data, and 1 for the ECC byte that is computed by the memory controller. And those DRAM chips are directly connected to the CPU by 2 different buses. The first bus is the 64-bit data bus that is actually split into 8 smaller 8-bit data buses between the CPU and each DRAM chip. And since the DDR4 data burst is 64 bytes, that means that at each burst of data on the DIMM module, each chip will receive 64 bits of data. And the other bus on the DDR4 interface is a control address bus, and this one is shared by all the chips. But on the registered DIMM, it goes through the RCD, which actually will distribute the command address bus to both sides of the DIMM, and this is important to remember for later. So now let's see what is inside a DRAM chip, a standard DRAM chip. So in all DRAM chips, the memory is divided into banks of memory. And a memory bank is just an array of memory cells, and those memory cells are simply capacitors, and those capacitors discharge over time, and then the information they hold will eventually fade, so they have to be periodically refreshed. So that's where the D in DRAM comes from. It stands for dynamic. And as you can see, the array of memory of a DRAM chip is accessed by using an address that is called the DRAM address, and it is composed of a bank group, a bank address, a row, and a column address. And this is the memory controller responsibility to translate a CPU physical address into this DRAM address. So now that you have a picture of how a standard DRAM chip is, let's see how our chip is different from this one. This is a high-level view of how our chip works. So you can see on the right top corner that the DDR interface actually allows to connect to two different types of things. It allows to connect to the DRAM array at the bottom, like any standard DRAM chips, but it also allows to connect to what we call a control interface, which is simply a 64-bit control register that allows us to communicate with the processor, the DPU, that are in the same bank as the memory. And it's important to note that the DPUs cannot talk to each other, so they can only work locally in their own bank. They can only have access to the 64 megabytes of data in their bank. Okay, so how is it possible to distinguish between the control interface and the DRAM array of memory? Actually, we achieve that by organizing the DRAM chip, our DRAM chip, this way. We have behind the bank group 0 and the bank group 1, 8 banks that contain the DRAM memory and their processor, their DPU. And we use the bank address 0 of the bank group 2 in order to address the control interface, what we call the CI. And the 7 other banks are not used in our product. So something else, our product is a register DIMM, and our register DIMM cannot have ECC byte because this is the memory controller responsibility to compute this byte when it writes data to the DIMM. And since we have processors that can modify those data and they cannot talk to each other or update the ECC byte, it is not possible for the memory controller to have a valid ECC byte at all time. So on the first version of our product, we do not have ECC chip on a register module. So now that you know all the particularities of our product, let's see how we manage to use our processors from a Linux user space application. And from now, we'll go over all the boot flow and detail all the roadblocks that we encountered to achieve this. And this is actually a photograph of how we started the bring up with, as you can see at the bottom, our DIMM, UPMEM DIMM, and one what we call legacy DIMM, which is a standard DIMM module. So first, let's start with some background with how the POWER9 boot flow works. This is a standard boot flow on the POWER9 platform. And you can see that we have to go through all those steps in order to reach the Linux, which is on the top, which is on the bottom right corner. And most of those steps are executed by Hostboot. Hostboot is the platform initialization firmware. And among other things, one of its responsibilities is to initialize the memory. And we think that it's important. And once Hostboot has finished its job, it will hand control to Skiboot. Skiboot is another piece of software that will install the runtime services for the operating system. And then Skiboot will hand control to a small Linux distribution that is called Skiboot, that contains a small bootloader that is a user space application that will finally allow to exec the real Linux on the platform. So now that you have this picture in mind, let's see what happens when we press the power button. Actually, we faced our first boot issue during the DRAM training, which is part of the memory initialization. So what is the memory training? So this is a picture of how the DIMM module is connected to the CPU, to the memory controller. And as you can see, the data bus and the command address bus have two different topologies. And then from the processor point of view, the DRAM chips will all be at different distances. So the memory controller has to account for these differences so that it can respect the DDR timings, and DDR timings are hard to respect because DDR4 is a very fast protocol. So for example, when a write operation arrives on the DIMM module, the memory controller will have to launch the address and the data with the correct skew between them so that the DRAM chip will receive them with the good timings. And in order to find out those timing, the memory controller will initiate some calibration step, and actually there is one of them that is problematic for our product. And it is problematic because the algorithm behind this calibration step needs to access real memory. It will write data to the memory and it will try to read them back while adjusting some timings. But what happens here is that it will try to access memory behind bank group 2 and bank group 3, where there is not any memory. So the calibration step fails. So we have to modify its behavior so that it does not try to address those DRAM addresses. But on a POWER9 platform, most of the calibration is done by a hardware engine that is called the CCS, and it's not possible to modify it. So that's when I decided to reach the community, and I used the Skiboot mailing list, and then I quickly got in touch with Stefan Glancy and Edgar Cordero. Stefan Glancy is a memory firmware engineer at IBM, and Edgar Cordero is a memory lab lead at IBM too. And Stefan developed the software equivalent of the problematic hardware calibration step, and then we succeeded in passing the calibration on our DIMM, but only on half the DIMM. And this actually was an unexpected result because of the RCD on a register DIMM, because the register on the register DIMM is responsible for distributing the addresses on both sides of the DIMM. And it will try to conserve power and reduce simultaneous output switching current by enabling what is called address inversion. What it means is that on one side of the DIMM, the calibration step will target real memory by targeting bank group 0 and bank group 1, but on the other side of the DIMM, the RCD will invert the address bits, and then it will always target the bank group 2 and the bank group 3, where there is no memory. And we fall into the same problem as previously, so the only way to fix that is by disabling the address inversion. We simply have to tell the RCD to not invert the addresses anymore, and again, Stefan and Edgar found some hidden setting in the documentation to tell the memory controller that there was no address inversion anymore, and despite of that, the calibration step were not successful if we disable the address inversion at the very beginning of the boot. So fortunately, we had the software equivalent of the calibration step, and then we were able to disable and re-enable the address inversion right during the memory accesses. And once the calibration step were over, we were able to disable completely the address inversion on our DIMM. And then we will avoid further problem with further accesses to our DIMM. So finally, we were able to go further into the boot process. And the next step where we failed was at the end of the memory initialization, at the very, very end of the memory initialization. And it actually happens when Hostboot tries to exit the cache. Because remember that Hostboot is responsible for initializing the memory, so it can't execute from there until it is done. So it will execute from the CPU cache that acts as a tightly coupled memory and not a normal cache. But at some point, Hostboot will need more space, and then it will try to jump into memory. And we imagine that the problem comes from the way the firmware maps the DIMMs inside the system memory between the 0 and the 4 terabyte addresses. And this is indeed how the firmware maps the DIMMs inside the system memory. And as you can see, the firmware will interleave the DIMMs with each other, and it does that in order to maximize the average bandwidth of the system. Because by doing that, the hardware will spread the physical contiguous addresses across multiple DIMMs, and then the access are parallelized. But we do not want our DIMMs to be interleaved with legacy DIMMs. We want complete control over our DIMMs. So we need to find a way to make our DIMM accessible by using a physically contiguous region that is not interleaved with legacy DIMMs. And then we have to go back to the step 7 of the boot flow, where Hostboot decides to group channels that contains our DIMMs with channels that contains legacy DIMMs. And then we can disable the interleaving, but again, the boot still fails at this point. So it is actually very simple. This is just because Hostboot load address is inside the first 8 GB of memory, and then it tries to execute from our DIMM, and then it fails. So the simplest solution to this problem is simply to swap the DIMM physically, so they are mapped this way by the firmware, and then Hostboot load address falls into a legacy DIMM, and then the boot can go on. And then we can encounter the next issue. The next issue is when Hostboot gives the control to the platform to Skiboot, which is responsible for installing the runtime services. And this is kind of the same issue, because Skiboot will need some memory to store some data, and Skiboot by default uses the end of the memory space. And at the end of the memory space, there was only our DIMM, so the boot of Skiboot failed. And the simplest solution here is to simply add a DIMM in the servers so that a DIMM is mapped after our DIMM. And Skiboot has some legacy DIMMs to store its data, and it's fantastic, and it can go on. And we finally arrive to the real Linux, and the real Linux fails to boot too, because the memory map that is installed by the firmware is passed to Linux by using a device tree, and there is no information in the device tree that our DIMM are special and that they should not be used by Linux kernel in its own memory pool. So we have to modify this device tree so that Linux does not touch our memory, and this will be our driver responsibility to map this memory region inside the kernel mapping so that we can use it later in our user space application. And once this is done, we have a fully booting Linux, a fully working Linux. So the only thing that is left to do is how can we address a control interface that allows to communicate with the CPUs? How can we target a specific DRAM next to the CPU that we are actually targeting? And the question is simply what is the function that maps the CPU addresses to the DRAM addresses? And of course, this is not documented, so we had to do some experiments to find this. And this is the mapping that we found on a POWER9 platform. So our memory region, which starts at 8 GB, is actually divided into blocks of memory whose length is 128 bytes, which is the size of a cache line. And the first cache line of our memory region will target the bank address 0 of the bank group 0. The next cache line will target the bank address 0 of the bank group 2, which is the control interface, which will allow us to communicate with the processors, and so on. And this pattern repeats all over our memory region. And then we know that to target we know that the first cache line of our region allows us to target the bank address 0 of the bank group 0. But remember that the command address bus on a DDR4 interface is shared by all the chips at the same time. So during any read or write operation, all the chips are targeted at the same time at the same address. So how can we specifically target a chip? How can we, for example, where do we have to write in the first cache line to target the first chip of the DIMM? First, you have to remember that the data burst on the DDR4 interface is 64 bytes long, so the cache line of a POWER9 platform will be split into two DDR4 data bursts. So this is only the picture of the first data burst that tackles the DIMM module. And remember that during a data burst on the DDR4 interface, each chip will receive 64 bits of data. So the first solution that comes to mind to write 64 bits of data to the first chip of the DIMM module is to write it at the address 0 of the first cache line of our memory region. So let's see what happens on the DDR4 interface. This is actually how this block is divided between the different DRAM chips that are on the module. And you can see that your physically contiguous 64 bit of data from a processor point of view is actually spread across the 8 chips. So the solution to fix that is to simply transpose the matrix, the 64-byte block, this way, so that the first column simply targets the first chip. So now we know how to write 64 bits of data into a specific DRAM chip at a specific address. So let's take a look at what happens at a byte level. This is a picture of the 8-bit data bus that connects the CPU to the first DRAM chip. And this is the value that we send first, which is DE. And actually, the DDR4 standard allows to swivel the data bus. And it is not a problem for real memory, but in our case, the processor that is inside the DRAM will not see the same value as the CPU. So it will obviously raise some issue. But we actually knew about this feature in the DDR4 standard. So we have in hardware what we call shuffling boxes that we just have to configure once, so we don't have to do this shuffling by hand at each transfer to the DRAM. Okay, so now we know how to communicate properly with our DRAM chips, so that should work. We should be able to talk to our processors and execute things on our processors. But actually, we had some issues with the write that targets the control interface. Remember our control registers that allow us to communicate with our processor. And to understand that, you remember that the cache line of a POWER9 platform is 128 bytes long, and then it generates two back-to-back data bursts on the DDR4 interface, and then it generates two back-to-back 64-bit commands on the control interface. And those two very close data bursts are not handled correctly by our control interface. Our control interface was designed for a 64-byte data cache line, which is actually current on all other platforms. So we had to find a way to increase the timing between those two data bursts. And again, this was possible thanks to Stefan and Edgar, which found the correct register to modify to increase the timing, and magically it worked. And that should be okay to use our processor, but again, we encountered another issue that is specific to the POWER9 platform. And the problem we had is that sometimes when we read the result that is exposed by the control interface, the bytes were correct, but they were shuffled. And this is actually due to a cache optimization that is called critical word first, that requests the missed word first from memory and send it back to the CPU as soon as possible. So for example, if the CPU tries to target the fifth word of a cache line, the cache will request from memory the fifth word first. It will not request the first word of the cache line first. And this allows to gain tens of cycles from a CPU point of view. So this is quite a good optimization. But in our case, we had to defeat this optimization. And The only way we found to defeat this optimization was to execute the reading of our control interface in an atomic context, so in the kernel by disabling the interrupts, and also by adding the proper memory barriers where it was needed. And finally, by doing that, we were able to communicate correctly with the control interface, and we were then able to launch our first hello world on our processor. So this is a screenshot of LLDB, which we use to launch programs on our processors. And actually, it requires a lot to work on our DIMM to be able to launch a program on our processors. To achieve that, we have to send command to reset the DPUs. We have to send command to load the program into the instruction RAM of the processor. And we have to send a boot order, and we have to wait that the program is actually finished. And once this is done, we have to fetch the string that it printed from the DRAM, and this allows to achieve an hello world. So this is not simple to arrive to this result. So that's all. The bring up was very, very interesting. We had some hard time finding the last bugs, but when they were found, so this was fantastic. So hope you enjoyed the journey, and thanks for attending. Do you have any questions? Yes.
Who built the DRAM chip with your processor in it? That seems like it would be a very expensive thing to do.
Yeah, so
Yeah, my boss can answer the question.
So, I mean, that's an interesting question because you know you have, I mean, this D1 silicon, you need a special foundry, and we are a fabless semiconductor startup, so we are doing it ourselves. And so, if you know the D1 market, you have 3 big D1 manufacturers. I mean, we are not working yet with them, but we are working with a smaller, Taiwanese D1 foundry, but we own one, which is you can buy the sisters DRAM, which are the same DRAM IP, but without processor in your local computer.
Any other question? Yes?
I missed the first 10 minutes, so sorry if you already answered it, but it sounds like this will be so much easier with OMI now coming.
Actually, OMI will only change the format of the DIMM module and the way we talk to the memory controller. But the technology is the same.
I will add something. I mean, that's still something interesting. I mean, of course, as you see, I mean, the DDR4 protocol was done to, the protocol was defined to basically replicate quite tightly how the DDR4 silicon is working inside. Of course, with OMI, I mean, if you assume that you can change or program the OMI bridge, yeah, you can do something better. Because here, for example, you have a CPU. At some point, it has results or things like that. And of course, I mean, you have no asynchronous way to answer. And with OMI, yes, you do. And you have, so, I mean, if you just use rawly modified OMI, sure, I mean, the only advantage is density. But of course, I mean, medium term, you can see a lot of paths where you actually take advantage of all OMI.
Thanks.
Do you also have this working on x86 platform, or do you only get it working on Power?
Yeah, we have x86 platforms that works, yes. And it was way easier to make it work on the x86 platform. Oh, yes, please.
So which kind of operations can you do in memory? So what does it support?
It's a general purpose processor, so you can do almost anything. So obviously some operations are more costly than others, but it's really a general purpose processor. So anything you want to do in it, you can do it. Yes?
Now it works. Is there anything we can do to clean it up? I mean, in terms of, even just at the tail end, in terms of avoiding the stupidity of both Opal and Linux picking the memory up and trying to use it and tagging it properly. I mean, is there patches? Is it in a state where we can get those patches
I'm in the process of cleaning these things with Stephen Glancy. He proposed for help, and then, yeah, we will obviously upstream these patches as soon as possible. Yes. Yes, please.
You replaced a bit of the hardware procedure with software. The first bug, the first.
Yes, the first calibration step.
You replaced something which was done in hardware by something which was done in software now.
Yes.
So first, it's lucky that you could do that. And second, why was it done in hardware? So what do you use?
Because I think that hardware is faster. But actually, we use a small step that is done in hardware, but we control it in software. I can't explain the details of the algorithm, but we need the hardware to do a very small step, and we just encompass it in software loop. Okay? But I think the hardware does that because it's simply faster.
Yeah, I mean, maybe we have to, I mean, basically, what he has explained earlier is using, this engine called the CCS, which is basically just some kind of state machine outputting, defined signals on those pins. And at some point, inside the state machine, it was doing a few steps we don't want to do the same way, so we are basically, instead of doing the full chain of steps, we are basically, cutting that stuff in smaller pieces, and we are still calling the smaller steps. But not basically changing all of that.
Okay, thanks. Thanks again. Merci.